Welcome to topology class. Today we will discuss the closure operators. Last class too we have discussed the closure operators and we have middle of a theorem. So first, let me list it out the theorem. It was 1.5 theorem. Theorem was, let X be a set let X be a set and theta from P of X to P of X theta from P of X to P of X, a function such that first condition was, for every A belongs to P of X, A is contained in theta of A. We will say that it is expansive operator. And second one was, phi is fixed, that is empty set is fixed point of theta. And third was, theta is idempotent. And fourth one, theta commutes with finite unions. If this is the case, then there exists a unique topology T on X such that this operator theta coincides with the closure operator satisfying these properties. So this was the theorem we want to prove, and we have proved up to where we have proved. Next thing we want to prove was, have you proceeded? Are you remembering this? First we will assume that theta is a your theta so proof structure, just I am noting down the proof only. Just since we have made all these comments in the previous class, we will define that theta from P of X to P of X satisfy the above four conditions. Okay, so assume such as theta exists. Assume theta with the properties 1 to 4 exist. Not exist. Okay. Now we want to find a topology on X such that for every A subset of X, theta of A is equal to A closure, right? So we want to prove there exists a topology script T on X such that condition is if A belongs to or A subset of X, comma, what you're having is theta of A is equal to A closure. So we want to prove this A closure with respect to, if you need means you can say that A closure with respect to this topology. So for that what we have done, first we have constructed a set script C. So let script C is equal to set of all A subset of X such that your theta of A is equal to A. Okay. And we will say that C has certain properties. What was the property? C has the property. We will say that first thing, phi an empty set belongs to C. Claim. We claim that phi an empty set belongs to C. And second thing, C is closed under arbitrary intersection. And third one is C is closed under finite union. Finite union. So we will claim these three conditions here. And we have proved that these three conditions, right? Up to that only we have discussed. Uh, so have you concluded that? So by theorem, so by theorem 1.2 means this closed collection of these sets satisfying these three conditions. The family T of complement of members of C or C script C is a topology is a topology on X. So by theorem 1.2, the family T of complements of members of C is a topology on X. Now what we want to prove? It remains to be verified that the closure operator associated with this topology coincides with theta. Coincides with theta. So this is the thing we want to prove. So what we are going to do is, let a subset of X, then a closure with respect to this topology is the intersection of all closed subsets of X containing A. But the closed subsets of X are closed subsets of X are, see here, let A subset of X, then A closure means it is the intersection of all closed subsets of X containing A by definition. Now we will examine what is the closed subsets of X. From the closed subsets of X are, with respect to this set C, how we can say closed subsets? It should be fixed points, right? So closed subsets of X are precisely the fixed points of theta. The fixed points of theta. Hence, A closure is equal to I can write intersection of all the subset B subset of X such that A is contained in B and next condition is B is closed. So instead of that I can write theta of such that theta of B is equal to B. Theta of B is equal to, so this is my state. Now whenever A subset of B and theta of A is contained in theta of B, monotonicity the reason is monotonicity, since monotonicity, so theta of A is contained in theta of B. So if A is contained in B and theta of B is equal to B itself, then we can conclude that theta of A is contained in B, right? But A closure is intersection of such B's, and so what we get? But A closure is the intersection of such B's, and so what are you getting? Theta of A is contained in A closure. Theta of A is contained in A closure. So you have got one way of inclusion, that is Next inclusion, we want to prove that A is contained in, or theta of A is contained in, or A closure is contained in theta of A. That is the thing you want to prove now. So theta of A is contained in A closure. For the other way induction, for the other way induction, we note that by condition 3, theta of A belongs to script C, while by condition 1, A is contained in theta of A. Hence, A closure is contained in theta of A, and that's equal to, okay, A closure is contained in theta of A. Now, A closure being the smallest number, being the smallest member being the smallest member. Since we are taking intersection of all closed sets, right? Member of C, strip C, containing A. Hence, for all A subset of X, theta of A equal to A closure. Theta of A is equal to A closure. Hence the proof. So we have proved the theorem. That means there is a one-one correspondence between such operations theta and the topologies. Now what about the other way of inclusion was there? That means if such a topology exists, then it will coincide with the closure operator. So that is a very trivial one. So I'm leaving for you. Now the converse part is trivial since A is contained in A closure. So we want to note some more things here. Let us see what and all we want to know. First thing is, as I have said, this theorem establishes a one-to-one correspondence between the set of all topologies on a set X and the set of all operators theta from P of X to P of X. Okay, so this is the first thing we want to note here. So as a note, not first one. This theorem establishes a one-to-one correspondence, a one-to-one correspondence between the set of all topologies between between the set of all topologies on a set X, on a set X, and the set of all operators, the set of all operators theta from P of X to P of X satisfying the properties satisfying the properties from condition 1 to condition 4. This is the first thing. Second note, the properties 1 to 4 are called the closure axioms, called the closure axioms. And this theorem is called an axiomatic characterization of closure operators. Axiomatic characterization of closure operators. Axiomatic characterization of closure operators. So this theorem can be asked as state and prove the axiomatic characterization of closure operators. Next we are passing to a definition. 1.6 definition. Let A be a subset of a space X. Let capital A be a subset, be a subset subset of a space X, of a space X, then A is said to be dense in X if A closure is equal to X. If A closure equal to X, we will say that A is dense in X. Not the entire set X, the entire set X is always dense in X, is always dense in X. Because when you're taking X closure, it should be X itself. Now we know that the evident thing Q is dense in R. So first thing, second one, in R with the usual method. Okay, that is in R with usual topology. What you can say is Q is dense. Q is dense in R. Q is dense in R. So these are the examples. Now 1.7 proposition. 1.7 proposition. A subset A of a space is dense in X. Space X is dense in X if and only if for every non-empty open subset B of X every non-empty open subset B of X, A intersection B cannot be equal to empty. That is, this is actually we are treating as a checking tool for some set to be given some set. We want to check that whether it is dense or not. So this is the checking tool for that. So what we have to do is we have to take an arbitrary open set in that and check whether it is having intersection with that arbitrary open set as non-empty. If a set is having non-empty intersection with all the open sets, then that set is going to be dense. Suppose Suppose A is dense in X. A is dense in X. And B is a non-empty, is a non-empty open set in X. Now if A intersection B equal to empty, then we can have A is contained in X minus B. Hence, A closure should be contained in X minus B. X minus B closure will come, but that is X minus B. What is the reason? Since B is an open set, X minus B is closed set. Closure of a closed set is that closed set itself. So it is X minus B. So A closure is contained in X minus B. Okay. But then X minus B is a proper subset of X. Cannot be equal to X, right? Since it lack A. Now, which is a contradiction? What's the reason? Because we have assumed that A is dense. So A closure should be equal to X, comma, which is a contradiction. Which is a contradiction. Since A closure is equal to X, we assume that it is dense. That's why. So what you're having is A intersection B cannot be empty set, right? Now conversely, assume that A meets every non-empty open subset of X. Open subset of X. This clearly means that the only closed set containing A is X, and consequently A closure should be equal to X. See, conversely, assume that A meets. So we are having a topological space here. Now our set is A. Suppose this my triangle shaped one is A. So in order to find its closure means I'm having the condition that all the open sets in this having non-empty intersection with A. So if these all are going to be open sets, everything is having non-empty intersection with A. That means these all points are going to be interior points of this. Now you want to check the closed set which containing A means I should consider all these points, right? All these points in all open sets. That means I will get A closure as X itself. So hope you understood today's theorem. So today we have discussed about closure axiom and a checking tool for a given set is dense or not, right? Dense means if a closure equal to X itself, then we will say that A is dense in X. Okay, with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.